Good morning, everyone, and welcome to the JKMRC Friday morning seminar series. On behalf of the University of Queensland and the Sustainable Minerals Institute, I'd like to acknowledge the traditional owners and custodians of the lands in which we meet today. We pay our respects to their ancestors and their descendants who continue cultural and spiritual connections with country, and we recognize the valuable contributions to Australian and global society. For this seminar, it is my pleasure to welcome Professor Kenneth Collerson. Ken is an Emeritus Professor at UQ and former head of Earth Science. He is an internationally recognized geologist, geochemist, with technical expertise focusing on discovery of critical metals, alkaline, gold, copper, porphyry copper systems, and specialist on regolith-hosted rare earth element systems. As a technical director for Victory Metals, he facilitated discovery of the North Stanmore heavy rare earth elements and Scandium, rich regolith deposits in WA. As Research and Development Director of Transitional Resources, he postulates a new metallogenic model for the Cloncurry region that allowed discovery of previous unrecognized copper, cobalt, gold, porphyry, and gold rare earth elements and wolframium epithermal mineralisation, a new mineral system in the Northwest Mineral Province. Today, he will present a seminar titled A World-Class Regolith-Hosted Heavy Rare Earth Element and Scandium Discovery above the North Stanmore Alkaline Intrusion in Western Australia. So let's give a warm welcome to Ken.
Thank you. Thank you very much, Daniel. It's really a pleasure to come and speak to you today about the North Stanmore deposit. We've been working on it for about a year, 2.5 years now. It initially started life as a gold project, but as you'll see, it has developed into something much more significant. Is this not advancing? Yeah, just get on. Okay. As there may be some commercial aspect to this presentation, I thought it was best to provide a disclaimer and then move on to the talk. Gilbert was very astute, and he recognised that the rare earths were something of quite significant value and political economic consequences with respect to them, because China controls a large proportion of the rare earth production, especially the heavy rare earth production. And most of the heavy rare earth production is coming from South China, from regolith-hosted systems. And as he commented, you know, that China has the bulk of the resources, and if you're trying to find some, what's the chances of succeeding? What's plan B? Well, if you can't become Chinese, then possibly plan B is not the Chinese part, but maybe it's Victory's North Stanmore dysprosium terbium discovery in Western Australia. We made this discovery about 1.5 years ago. Now, while I cover this topic, people are very familiar with Mount Weld. Mount Weld, Linus's deposit, is a hard rock deposit, hard rock carbonatite deposit. A number of the other developing mines are also hard rock deposits. Now, there are a lot of differences between hard rock deposits and regolith deposits in terms of capex and opex. Most of the regolith deposits are in China and Myanmar, and in fact, China is exploiting Myanmar regolith right now. There's new sources being discovered in Brazil, Chile, Africa, and now in Australia. Hard rock deposits, principally Bayan-Obo in China and other Chinese carbonatites, together with Mount Weld and Mountain Pass in the United States. The difference between the regolith deposits, particularly the Chinese deposits, is that they are heavy rare earth rich. Some of them also contain light rare earths, but some of the Brazilian regolith deposits, but the dominant source of rare earths is coming from the heavy rare earth deposits in South China. Hard rock deposits are dominated light rare earth rich because they are carbonatites, and they have high ratios of neodymium, praseodymium, two light rare earth elements, to dysprosium, terbium, the high value heavy rare earth elements. In terms of exploration costs, Shallow air core and RC drilling will get you most of the information you need for regolith deposits, whereas the hard rock deposits require deep RC and diamond drilling to exploit the resource, to test the resource. In terms of mine development, you're looking at maybe $100 million for the capex for regolith deposits, whereas hard rock deposits are requiring about almost $1 billion. Metallurgy, the regolith deposits require very simple leaching because the primary phases have been broken down by oxidation, whereas in the hard rock deposits and placer deposits, the primary minerals require complex metallurgy to extract the rare earths. And finally, in terms of environmental aspects, because the regolith deposits are developed as a result of oxidation and groundwater movement, in many cases, the actinides have been moved from the system and they are removed. Whereas hard rock deposits and placer deposits often have a high uranium and thorium content to deal with. So North Stanmore discovery, what have we found? We've got a regolith-hosted heavy rare earth and scandium deposit. We've got a mineral resource estimate that's been reported. It's both indicated and inferred. The indicated is 149 million tonnes. The indicated plus inferred is 253 million tonnes. We have within the deposit about almost 80,000 tonnes of rare earth oxides and 28,000 tonnes of heavy rare earths. The deposit, it's Australia's richest heavy rare earth system, regolith system with 35% heavy rare earths. That is europium through to lutetium. It also contains hafnium, cobalt, nickel, copper, and gold. It has scale, grade, and value. And this map on the right-hand side of the screen indicates some of our drilling system that we've based the resource estimate on. We're now doing further drilling to expand the resource. So the regolith system is developed over an alkaline intrusion. Now, alkaline intrusions are very important because they are the conduits that bring these critical metals from their mantle source to the lithospheric crust. It's a very large system. To put it into perspective, here's a map of Brisbane, and our resource extends all the way from North Brisbane down to Forest Lake. It's a huge system. The system consists of two domains, essentially subparallel domains, a high-grade system at the top, containing about 46 million tonnes, averaging about 1,000 plus million tonne rare earth oxides, and then a large indicator resource of about 149 million tonnes of 532 ppm, but with a very high ratio of heavy rare earths to total rare earths. And as you can see from a bit later in the presentation, we've cracked the metallurgy. We'll be able to extract up to 80 to 90% of the rare earths. The deposit is enriched in a number of elements. Not only do we have dysprosium and terbium and praseodymium and neodymium, we also have significant thulium and lutetium, which are critical metals that are less focused at the moment in terms of applications. They have mainly military applications, and hence the United States is very interested in what we're producing. Scandium is also a very important element. It's been referred to as the runt of the rare earth litter because it occurs in group 3 of the periodic table, the same group that the lanthanides occur in. It is a very high value product, generally associated with mafic alkaline systems. And in our case, because we have a mafic alkaline system, we've recovered significant amounts of scandium. In addition, we have hafnium and cobalt as byproducts, and nickel and alluvial gold. So what I'll do in this presentation briefly is run through a number of points. Now, first, one of the important things in mineral exploration is seeing what other people see but thinking what no one has thought before. Don't just follow the herd. Think laterally. And that was Roy Woodall's view, and that's why Western Mining Corporation was such a successful operation. That was the view that we took at North Stanmore. Initially, Victory was Victory Gold. They were looking for gold. I was asked to give them some advice concerning their PXRF data that they were getting, and I noticed that they were getting, and the managing director also had previously noticed some values of yttrium coming up. And he approached me and said, well, what do you think? And I said, well, I think it might be something quite interesting. And that is history now. So what I'll do in this presentation is run through some of the technical aspects of clay deposits. I'll then run through some of the geological aspects of the North Stanmore regolith-hosted rare earth system. I'll look at the geochemical affinity of the North Stanmore intrusion that shows that it is an alkaline intrusion. We'll then talk a bit about the background to rare earth chemistry. It's one of the problems that I see, particularly in many of the ASX announcements, is that the people who are writing those announcements have very little knowledge of geochemistry, particularly when they list the rare earths alphabetically. I'll then talk about the rare earth and scandium systematics of the regolith. I'll show some of the ChemScan work that was done at the JK Centre. Then I'll touch very briefly on the beneficiation and metallurgy that we've obtained through core resources in Albion. And then finally, a little bit about evaluation metric for rare earth deposits. So what do we see there? In a regolith system, what we see is a system of leached pedolith, saprolite, saprock, and then bedrock. What we see as we look at the geochemistry of that leach profile is we see a rather interesting thing. In acid soil waters where pH is less than 6, the rare earths, particularly the trivalent rare earths, are leached in solution and they migrate downwards in the weathering profile. At the same time, the 4-valent cerium is more resistant and stays higher in the rare earth profile. And so you get a system where the upper part of the regolith is characterized by a cerium anomaly greater than 1. The lower part, the more interesting trivalent dominated system, has a rare earth as a cerium anomaly less than 1, and the saprock and bedrock have cerium anomalies of 1. The cerium anomaly is actually the key exploration vector for finding valuable rare earth systems, and it is an indicator of regolith-hosted rare earth systems. So what does it mean? What's this cerium anomaly? Well, I'm going to show a chondrite normalized plot. This is very important because, and I'll come back a little bit later in the presentation to this in detail. This is what happens on a chondrite normalized plot where you've got a positive anomaly in cerium. When you go from lanthanum to praseodymium, there's this spike. What this is the sample is divided. The sample concentration is divided by the concentration of rare earths in the chondritic meteorites. And you get this smooth pattern for most of the rare earths, but a spike here. That's a positive anomaly. This is the equation that enables you to calculate that. It's a very simple equation. These are the chondrite values that I've indicated here. So cerium anomalies greater than 1 reflect the gain of cerium 4+. Cerium anomalies less than 1 reflect loss of cerium 4+ and enrichment in the profile in the valuable trivalent rare earths. All leachable ionic clay deposits have cerium anomalies less than 1. In many cases, this is not appreciated by companies doing the geochemical reporting. So this is what the system looks like from North Stanmore. On the right-hand screen, your left, we have air core drilling samples from top to bottom. This is down to saprock down here. This is various saprolite layers. And within this, we have zones that show strong rare earth enrichment. Why do we have these enrichments in the North Stanmore area? Well, that's a very interesting point. Marco Fiorentini at University of Western Australia published a paper in Nature Science Reports in 2020, where he speculated the presence of a plume track extending from Mount Weld through to Kew. Now, plume tracks are very important because plumes, mantle plumes, are the conduit that bring metals from the mantle to the crust and lithosphere. So this is a zone which has operated probably over Proterozoic time from Mount Weld, where there's a stationary upwelling in the mantle, the crust has drifted across it, and along that trend, we find alkaline intrusions. We find the Mount Weld intrusion down here, the big carbonatite, a number of other carbonatites around Mount Weld. We also see carbonatites at Yttria, Redlings, and Jupiter down here near Kew. And then we see kimberlites and various other lithologies along this trend, and those were pointed out by Marco. When Marco published this paper, he was unaware of what we'd found in the Kew area. So the alkaline system is lying on a plume track. It has a very distinct magnetic character to it, which you can see on this image here. It's open to the north, it's open to the south, open to the east and west. It's a huge system. It's about 16 kilometers long, 4 kilometers wide, hence the overlay from north of Brisbane down to Forest Lake. It's a big system. It's post-tectonic, Proterozoic, almost certainly Proterozoic in age. We've drilled with diamond core drilling down to 250 meters into the intrusion and recovered a range of ultramafic, mafic, and silicic lithologies and minor carbonatites. It's very similar in geological character to the intrusions on the Kola Peninsula in Russia. That's an example of one of those big intrusion, complex lithologies, and also to the intrusions that I reported from Western Queensland, the Diamantina intrusions. This is what it looks like in thin section. Very characteristic occurrence of this brown amphibole, chaosutite, which is a characteristic feature of alkaline systems. Bits of phlogopite. This is an olivine bearing pyroxenite. We find carbonatites, we find gabbros, diorites, monazonites, cyanites, and rare alkali granites and minor carbonatites. A little bit of xenotine we also see in thin section. Some of the gabbros have nice subophytic textures. They're not deformed. These are post-tectonic and therefore younger than the Archean host rocks that surround them. We find iron-rich almandine garnet. We find evidence of sodic amphibole, which is characteristic of alkaline systems. Chromite, backscattered electron image of chromite, and also the presence of manganese ilmenite. Ilmenite, 9-titanium oxide, when it's rich in manganese, is a characteristic feature of alkaline systems. In terms of the character of the intrusion, there are a variety of ways of identifying whether or not it's alkaline. One of the ways is to use potassium silica diagrams, but in older rocks, potassium and silica can sometimes be mobile or overprinted. And so another discrimination plot was suggested by Julian Pearson Hastie, published in Journal of Petrology, using thorium as a proxy for potassium and cobalt as a proxy for silica. And on that diagram, we've got the field of the alkaline rocks and subalkaline rocks and thallitic rocks. And you can see where the the intrusion of the North Stanmore intrusion diamond core is shown here in the crosses, and they overlay quite nicely into the alkaline field. We also see a nice trend in a so-called variation diagram or Harker diagram with cobalt and nickel variation, varying from the perutites and peroxenites shown in the purple ornamentation through to peroxenites in green, orthoperoxenites, the cross, down to the more silica-rich differentiates, the intermediate and high silica differentiates at very low levels of cobalt and nickel. So the intrusion is a fractionated alkaline ultramafic to felsic intrusion. We can also use geochemical traces to show the affinity of the intrusion. This is a plot, this is a table showing two elements, niobium and tantalum. Niobium and tantalum and the niobium-tantalum ratio are particularly robust provide particularly robust records of the source lithology that they occur in. And here we see group 1 kimberlites have niobium and kimberlites have niobium-tantalum ratios of about 15. That's a typical mantle plume signature, alkaline signature. Carbonatites have somewhat higher niobium-tantalum ratios because they're rich in niobium. But as you can see here, that the Mount Weld carbonatite, a ratio of 155 niobium-tantalum, very similar to the ratios that one has been reported for the Silcrete, the Ferrycrete, and the regolith at Mount Weld. So this ratio, and here the kimberlite regolith has a ratio of 15. So these basically are plume-like signatures. And that's important because when we look at North Stanmore intrusion, we see that a very strong peak at a ratio of 15. Continental crust has a ratio of about 10. So this is not in anything to do with 10 to 11. So this is nothing to do with crustal components. It's a typical plume signature. And for other plume end members, the Ocean Island basalts, Mount Cameroon and Heard Island, you can see have these elevated niobium-tantalum ratios. So this is one of the vectors that we use to say, well, you know, this is an alkaline system. The interesting thing is when we look at the niobium-tantalum ratio for the regolith at North Stanmore, we see that it has a mean niobium-tantalum ratio of about 15.8. And that's a plot of depth versus niobium-tantalum ratio. Continental crust has the niobium-tantalum ratio of about 11. So what we're seeing here is a very similar niobium-tantalum ratio through the entire regolith column. The regolith column can be up to 80 to 90 meters thick in this area. And this indicates, this constant niobium-tantalum ratio indicates that the regolith is an in situ regolith. It's not a transported regolith. And that's a very important point. Now, I'll touch very briefly on rare earth chemistry, just a couple of points, because that relates to the way you interpret data. Rare earth abundances in rocks follow two trends. There is an absolute decrease, there's a decrease in abundance with increasing atomic number. So from lanthanum through to lutetium, the rare earths decrease in abundance. And this is called the lanthanide contraction. The other thing that we see with the rare earths is that, as described by the Otto-Harkins rule, is that even atomic numbers elements are more abundant than odd atomic number elements. And that's why we use chondrite normalized plots. And I'll show you that in a second. Most igneous rocks have yttrium-holmium ratios between 24 and 27. If they deviate from that, it indicates that fluorine has played a role in fractionating the heavier earths during, or oxidation can fractionate the rare earths. So chondrite plots also provide very useful QA and QC information for large data sets. So this is why we use chondrite plots. This is data from North Stanmore, one of our infill holes, 42 to 33 meters. On the first diagram, I've plotted just simply concentration with, on the bottom axis, the x-axis, increasing atomic number from lanthanum to lutetium. And you can see this sawtooth pattern you get reflects the Otto-Harkins rule. That's eliminated if you divide the concentration by the chondritic value, and then you see the true pattern of the rare earth distribution. And in this case, we have a very strong negative Cerium anomaly, which you can see here, 0.07. This sample is very heavy rare earth rich, 65%. It has a niobium tantalum ratio of 22, plume-like. It has a essentially chondritic yttrium-holmium and zirconium hafnium ratio. So this is a clear indication, again, of the alkaline affinity of this system. So this is a plot, a chondrite plot showing some of the different rock types we've recovered in the diamond core. And these are fields showing the different rock types and their variation in terms of chondrite normalization. The peridotites and peroxenites are at very low levels of rare earths. It increases gradually going upwards, with the nepheline cyanites showing the highest levels of rare earths. And then deep in the regolith profile, we see this zone of very significant enrichment, which may well be a hydrothermal alteration zone that's had weathering effects superimposed on it. We also see some samples that show exactly the same fractionation pattern as carbonatites. The fields shown here are carbonatites from the Kola Peninsula. You can see the data from the North Stanmore regolith parallels those beautifully. So it indicates that there are carbonatites in the system, but those carbonatites must be very rare because they don't influence the overall bulk ratio of heavy rare earths to total rare earths. If they were abundant, we would get much lower ratios of heavy rare earths to total rare earths. We see also variation in the system in weathering. So the Khaki field here is a set of data from basalts in India. The field of primary igneous rocks is shown in green, and the data from the North Stanmore regolith shows a huge variation in yttrium-holmium ratio, and that is due to oxidation, probably almost certainly yttrium variation during oxidation. So how do we also see this reported in the geochemistry of the samples? So there's our core samples, and this is a plot that was developed very recently by Cho and Hotto, showing N-member compositions, mafic, felsic, and soil, and it shows the variation that we see from fresh rocks through to soil. And this shows the entire data set for the North Stanmore system. So it's indicating that we have both felsic and mafic components, and they're gradually weathering, and the amounts of silica, aluminium, iron, sodium, etc., are gradually varying as we approach the weathering boundary and then into the sap rock. So this is typical of humid weathering. We've also looked at the hyperspectral mineralogy of the core from a number of holes, in fact, from pretty much all of our holes. In pink, you see the field of low crystallinity kaolin, and then in red, high crystallinity kaolin. Then deeper in the system, we see montmorillonite, white mica, chlorite, and then in the sap rock, we see iron, magnesium, smectite coming in. And this hyperspectral imaging enables us to map the alteration profile. And all of our ore deposit, all of our mineral systems lies largely in the low crystallinity kaolin field and high crystallinity kaolin field. To get an idea of how weathering may well have affected the rare earth abundances, I've selected here samples that have Cerium anomalies of 1, which essentially represent the source rock. So they're from the sap rock and primary compositions, and they lie completely in the field of fractionated alkaline intrusions. This was a very useful diagram published a number of years ago, 1972, showing lanthanum ytterbium, which is a light rare earth to heavy rare earth ratio, against total rare earth concentration on the x-axis. And then on that, I've identified fields of different rock types: hydrothermal fields, A-type granites, carbonatites, and fractionated alkaline intrusions. And you can see that the majority of our samples plot very closely into the alkaline intrusive field. Once again, supporting the view that the North Stanmore intrusion is alkaline in character. In samples that are rich in the trivalent rare earths, there is a shift in total rare earth concentration, with some samples even getting up to about 1% total rare earths. Very, very extreme, but averaging somewhere around about 500 to 800 parts per million. 1 or 2 samples lie down into the hydrothermal field. This is probably just simply an artifact of the enrichment process that took place during the weathering event. When we see what is the depth variation with weathering, these are samples with a cutoff of 400 ppm. They have a heavy rare earth to total rare earth ratio of almost 40%. We see a saprolithic regolith that varies from 10 meters to 75 meters. And then as we approach the base or the sap rock field, we then see a reduction in the overall variation in the total rare earth concentration, somewhere between 200 and maybe 500 parts per million in the sap rock and host rock. Putting that into perspective in terms of the Cerium anomaly, this shows the distribution of data. On this side of the screen, we have the area of positive 4+ gain. So Cerium anomalies range up to maybe 20, 30. On this side of the screen, we have Cerium anomalies where we have Cerium loss, and these are the samples that are enriched in the valuable trivalent rare earths. It's these samples that are the ones that should be sought after for processing for metallurgy. Another interesting feature that we see in the weathering profile, and this has not been reported previously, is that we see variation in the enrichment levels in different parts of the regolith profile. We see, for example, in these samples, these were some diamond drill core samples through the regolith. We see an enrichment about 12 meters, one at about 46 meters, another one at about 55 meters. And those are consistent with zones of either Cerium loss or Cerium gain. You can see that the sap rock is characterized by Cerium anomalies of 1. So what we see in different drill holes is different levels of enrichment. This sort of stacked weathering profile, and that has not been reported previously from other regolith-hosted rare earth systems. We believe these represent different oxidation events. And so North Stanmore contains multiple zones of heavy rich ore bodies. And these stacked events probably reflect the effect of variations in groundwater during different humid weathering events. So I've plotted a number of these zones on a chondrite normalized plot. We see one at between 15 to 25 meters, 28 to 37 meters, 41 to 46 meters, 53 to 77 meters. And note, they all have this negative Cerium anomaly. Paulo Vasconcelos did some very interesting age dating of the regolith weathering dating the regolith profile in the Yilgarn block. And he interpreted a number of ages, one between 65 and 80 million years, 50 and 30 million years, and 16 and 5 million years. And I think that what we're probably seeing here in this very thick, long, and continuous regolith profile at North Stanmore is a manifestation of fluctuation in tropical weathering events that shifted the groundwater water table over time. These would be very interesting to obtain age dates for these different zones to see how they correlated with Barlow's interpretation. I think it's probably quite correct. We also see in the North Stanmore system significant scandium. Now, as I mentioned, scandium has been referred to as the runt of the rare earth litter. There's quite an extensive literature now developing on scandium because it's a very high value element that is a substitute for titanium. It can be welded with magnesium. It forms a very nice component of MiG jet aircraft airframes, and China and Russia control the global supply. So it's a critical element. North Stanmore, we have significant enrichment. The average concentration of scandium in the crust is about 12 ppm. So you can see we have enrichments in the North Stanmore regolith averaging around about 80 ppm. It generally is considered to behave a little bit like the nickel, cobalt, and copper due to a smaller onic radius. And it's generally believed to behave differently to the rare earths, but we have data from North Stanmore that suggests that this interpretation may not be entirely correct. We see, for example, here that we see this scandium enrichment in the regolith profile corresponding to the same depths that we saw the scandium, the rare earth enrichment taking place. The enriched or the residual regolith is shown here. Some of these samples have upwards of 100, 130 ppm scandium. So scandium is probably being incorporated into goethite or manganese oxides. And this observation could have significant exploration implications. So we've done quite extensive drilling. We've drilled several extension holes. This one about 8 kilometers north of the mineral resource estimate area. There we encountered a very significant zone of high scandium, high dysprosium, high terbium, and high neodymium and high praseodymium. So this area gave us the first clue that the deposit may be much bigger than previously thought. And we're now currently doing further infill drilling in this region. So what's it look like in terms of the mineralogy? These are some backscattered electron images at different magnifications where we see kaolin, Mn minerals, manganese oxide minerals, and within them we see grains of rare earth minerals preserved. So the scandium is probably tied up with the manganese oxides, but the rare earth minerals can be imaged using backscatter electron imaging and also EDS. We see some of them contain lanthanum, niobium, neodymium, phosphorus, and yttrium, and this is almost certainly rhabdophane. But what we find is in the system, we find evidence of relic monazite and xenotime. We find rhabdophane after monazite, and we find churchite after xenotime. These are the key minerals that host the rare earths. They're key because they are low in uranium and thorium, because they're oxidized hydrous phases, and the uranium and thorium has been leached out of the system. We also see a little bit of ceriumite, which is the cerium 4+ phase. We see evidence of variation in mineral content with grain size. This has been part of our beneficiation testing, QuemScan data. So here's the 100 micron size samples. We find higher concentrations of rare earths in the finer grain material and higher concentrations of ceriumite in some samples. When we do beneficiation testing, the the solid samples on this conjoint anomalous plot are the head grades, and we see an increase in overall rare earth abundance by simply doing a separation of the minus 53 micron material. And that allows us to increase our grades quite substantially, up to 90% increase in grades. And so the mineral proportions that we see in the minus 53 micron fractions are cerianite, xenotime, trace from the relic phase. We see a bit of monazite, we see rhabdophane and churchite, and then other rare earth phases, and then a variety of more silicate-rich phases. So when we do the beneficiation, this is our head grade sample with 672 ppm. Our beneficiated sample ends up with a total head grade of with a total grade of 1276 ppm, and we see relatively similar heavy rare earth to total rare earth ratios, but importantly, the very high levels of dysprosium and terbium, and neodymium and praseodymium. We've done metallurgical results using a variety of lixiviants, initially using the tried and true Chinese method of ammonium sulfate with various pHs. We've achieved extremely good results, as you'll see in a minute, with samples ranging with head grades between 1600 and 1000 ppm. All these samples have very significant enrichment in the trivalent rare earths. And this shows an example of what our first test results are the blue results. We got good yields of the heavier earths. We then subsequently changed the lixiviant and to magnesium sulfate, sulfuric acid system. And you can see we got 90% recoveries of the heavier earths. We reported this to the ASX in May this year. In addition, we also recovered 50% scandium without even trying. And then most recently, and this is proprietary data, we've repeated the experiment with a different lixiviant, and the final recoveries we're getting now in the green is quite good, because that lixiviant will give us a very much significantly lower capex and opex for the extraction process. We won't be doing heap leaching, it'll be done in contained leaching environments. We've actually produced a rare earth carbonate, one of the few companies that have done so. That rare earth carbonate contains about 96% heavy rare earths. It also contains very low contents of iron and aluminium, and very low levels of thorium and uranium. So we're clearly on the way to commercialization. Another company has also produced a rare earth oxalate. This is Sierra Verde in Brazil. They produced an oxalate, we produced a rare earth carbonate. You can see from the pie diagram, the Brazilian example is much more enriched in the light rare earths, neodymium and praseodymium, as opposed to the North Stanmore rare earth carbonate, which is more significantly enriched in dysprosium and terbium. The rare earth carbonate from North Stanmore, enriched in dysprosium and terbium, they are the high value rare earths. So comparing rare earth data from several other regolith systems, I've shown here in purple the North Stanmore data. In the open cross is data from Uganda from ionic rare earths. Penco from Chile in the yellow dot. Sierra Verde from Brazil in the green triangle. Caldera in Brazil in the solid diamond. And then China, very low level. And then Madagascar. All of the rare earth, all these systems show negative europium anomalies. They show variable europium anomalies depending on their source rock.
So how do you value rare earth deposits? This shows a plot of some of these plotted on a typical diagram. They vary in grade, they vary in ratio of dysprosium, terbium, and they vary in thorium content. The main value from rare earth systems, from regolith systems, comes from the high value elements, dysprosium, terbium, neodymium, praseodymium, and scandium. Not all systems contain scandium because the regolith systems that are developed over granites are scandium poor. This shows a comparison of several of the deposits that we regard as peers, meteoric, MEI, VMM, Emeritus rare earths in Brazil, IXR in Uganda, BRA, Brazilian rare earths in Brazil, and Victory, VTM. And you can see the variation that we see here, predominantly IXR in Uganda and Victory are the two scandium bearing systems. This shows the market cap for some of these systems. This is the share price change that we've seen in these in the last year. Most have gone down. The two that have gone up are Victory and Brazilian rare earths. If you want to make an estimate of our mineral resource estimate has been based on 8% of our tenement area, and that yielded 248 million tonnes. If you extrapolate that to 100% of the area, then you're looking in terms of billions of tonnes. It's a huge system. And how do you value it? Well, I have a paper under review at the moment in Ore Geology Reviews. I was hoping to give a talk of this at the Critical Minerals Conference in Brisbane, but I was only given a poster, so I decided to withdraw it. This shows a plot of grade versus value of heavy rare earth oxides in US dollars per kilogram with the bubbles, and then the resource size. This shows North Stanmore, IXR Makutu, the Madagascar deposit, Pela Ema in Brazil, and Tenko in Chile. And if you extrapolate, and China is down here, very low grade, but very high tonnage. If you extrapolate the Victory's tenement area to 100%, then you're looking at a very, very huge deposit. And so we also have very low levels of uranium and thorium, as opposed to the other systems. So the takeaway message is really, we've discovered really a very significant regolith-hosted rare earth system in Western Australia. It's the largest indicated resource of any Australian clay-hosted system. It also contains other elements like hafnium, cobalt, nickel, and gold. Mineralisation is open in all directions. 8% of the exploration area has provided us with an indicated and inferred JORC resource that contains significant tonnages of dysprosium and terbium, neodymium, and praseodymium. We've confirmed the leaching metallurgy, and we have an offtake agreement negotiations well advanced. And I guess, you know, in academia, one likes to rank research output according to various metrics. Well, in terms of my H factor, my H factor is about 63, 64. That means 64 papers published, cited more than 64 times. In the commercial world, the way of looking at that may be to look at how a share price has varied over time. This shows the growth of Victory's share price over the last year. It's currently sitting between 39 and 40 cents. It's had a 90% increase. And compared to other rare earth projects, back to there, only a few have succeeded in maintaining that positive trajectory. Victory, Brazilian rare earths, American rare earths, and venture minerals in the same plume track area as Victory's deposit. All of the others have, over the last year, have lost value. And it's interesting in terms of, and I'll just finish up with this point, the ones that have lost value tend to be the ones that are more light rare earth enriched. It's going to be difficult to see how some of the light rare earth enriched regolith hosted systems particularly could compete with the neodymium and praseodymium production from Lynas. And I'll leave it there, and thank you very much.
Right. Thanks, Kent. A very interesting talk. Technical, as a geologist with petrology, mineralogy, and geochemistry background, super nice to see your presentation, and it's a nice discovery. I remember when I was a PhD, I was working there on the microscope. I think he was also on my side looking some of those samples and some monazite. It's quite cool to see what is turning out. I'm gonna give a quick question. So you show like those alkaline systems, and you see like most of the regolith is just below the topsoil, right? Do you have like good radiometric response from this topsoil?
We see a radiometric response, but basically the uranium and thorium content in the topsoil produces the gamma radiation, and that won't necessarily reflect what's below it. If you're in a glaciated terrain with fresh rock exposed, then you may see a nice radiometric response for the intrusion, but I think it's masked by the weathering process that's taken place. And you know, there is a very thin layer of soil and petalith above the intrusion that really provides most of the gamma ray indications.
Another question is like you showed how extensive it is, the enrichment and like even the tenement that you're showing. And at least on my understanding, most alkaline intrusion, they are not that large. At least like from what I know. Why do you think it's like such an extensive system?
Oh, some of these plume track intrusions are huge. In the Kola Peninsula, they're 20, 30, 40 kilometers in diameter. That's a very characteristic feature of some of these complex multi-component alkaline systems. The same is true for the Diamantina intrusions in Western Queensland that are about 80 meters down, 800 meters down, but they're also very large bodies. No, the alkaline dikes tend to be minor, but the major plutonic component tends to be quite large.
And just the last question is like you showed also there's still a lot of drilling and resource estimation to be done in the tenement. Do you expect to be something more homogeneous, or you expect to see heterogeneous a lot?
From the fact that we've already done extension drilling and we know what to expect distal from the resource MRE, we expect we'll see a very similar pattern emerging, but that will have to wait for a future ASX announcement.
All right, thanks. Any questions on the audience?
Thank you very much for a most fascinating talk. I must admit, as a metallurgist, my geological knowledge is about 40 years old when I did it at undergrad. But the metallurgist in me is going to ask, the two questions, if I may. What will the saleable product be once you've got a plant up and running there? And you mentioned copper, nickel, gold. Would there be any purpose or any financial advantage in going for that as well, or do you just see this as a rare earth operation?
They're very good questions. In terms of the saleable product, we could achieve a saleable product with our basket of just mixed rare earth carbonate at maybe a 20% discount to the value of metals in that product. That would then go on to a processing facility where oxides would be produced and then ultimately metal produced. At this stage, we're exploring all avenues for further processing of our rare earth carbonate. And so I can't really speculate at the moment, but obviously we're looking at trying to achieve the maximum return for our shareholders, and that would ultimately be getting to the oxide and metal stage. In terms of the second question, yes, we are certainly recovering in our flow sheet that's been developed at core a nickel, cobalt, a copper concentrate, and we will process for gold before we do the initial leaching because there's a lot of alluvial gold in the Q area. So those will be additional components.
Then we just have one online question from Rex. He was asking, on one of your graphs, you show ore resource on the x-axis on the bubble chart. What do you mean? Is this the indicated and inferred mineral resource, or do you have a PFS, and is this an ore reserve?
We don't have a PFS or reserve at this stage. The PFS is being undertaken at the moment by Mincor and will be released probably in maybe 2 to 3 months' time, with certainly by the end of the year, we hope. The resource size were based on published data released to the ASX on the quoted MREs from different companies, and ours was based on our mineral resource estimate that was released to the ASX several months ago. Yeah.
Any questions? So I have a more technical question. Sometimes like doing mineral characterization on rare earth can be quite challenging. And what's your workflow and routine that you usually approach to do this from petrography, automate mineralogy?
Well, I'm one of the old guard. I still use a petrographic microscope, and I use it in association with an EDS system, benchtop SEM with an EDS system on it. For some of these, the rare earth phases, this is critical, particularly if they're very fine grained. But with respect to the clay systems, then yeah, we've got a lot of benefit from using QuemScan at the JK Centre, and we've had several contracts completed here. So yeah. I think mineral characterization is one aspect that many companies don't go into. I think it's very important that one tries to get an idea of the grain size and mineral phase variation within the system, and that's why we approached it from the QuemScan perspective.
And you define out like the hyperspectral data that you showed. Sometimes you can also get out some, at least as far as I know, you can get some response from monazite, or did you get something of it, or was it basically clay?
Levels sufficient to get it. In a hard rock drilled sample through a carbonatite, you'd probably see it, but not in the regular.
Yeah, that's nice. So
we're just going with basically using the hyperspectral data to characterize the different saprolite fractions. We are going to systematize our regolith logging using some external consultants, and we're hoping that we are able to see with the external very careful logging, we may be able to identify, together with the PXRF, which we use all the time, some characteristic in the logging that indicates the rare earth rich zones as opposed to the non-rare earth rich zones. Just
one last curiosity question is, when you do the diamond drilling on this regolith, how's the recovery of the cores?
It was very carefully done, and the recovery was quite good. Yeah. We particularly use the diamond drilling to establish the density, specific gravity of the regolith.
All right. Any other questions on the audience? Otherwise, I'd like to thank Ken again for his very interesting presentation. Thanks, Ken.
Thank you.
Next week we have John Atherton from Acacia Energy presenting about renewable compensation in 2024. So I hope to see you all next week.